Can you all hear me? Yeah, okay, perfect. So, waves, ice, marginal ice zone, like that's basically the title. I don't even remember what I put in there, but that's what I do. Mostly I work in the Southern Ocean stuff, even if I'm at the University of East Anglia, which is in Norwich, about 60 miles that way, like 90 kilometers. It's not in the United Arab Emirates, as some people confuse it. And I'll present some of the mathematical modeling that I've been doing there with the median when I started in November. But I just wanted to start from a little bit further south. And this is a picture here, and then I'll show a video that I took from the South African icebreaker Agalas 2 a couple of months ago, on the 24th of July 2022, as part of in the Southern Ocean at 49 South during the Southern Ocean seasonal experiment. And while most of you here in England were like enduring a heat wave with 40 degrees, there it was a little bit cooler. And now the nice bit that I didn't want to spoil is this one. So waves and sea ice, that's it. I'll let you appreciate that. I hope you don't get seasick. And how big do you think the waves were? Four and a half. Yeah, we had a boy next boy. So yeah, it was rocky in the ice. There are waves in the ice. It's not a flat surface. Okay, moving on. And so like one of the standard definitions that Vernon mentioned in his introduction was like that the marginal zone is that area of the ocean of the sea ice exposed to the open ocean. In my case, I care about waves, which is in between the pack ice, the compact ice, and the open ocean. And there is a lot of interesting and complicated physics, and that's what we try to understand, both from a physical point of view, albedo, melt points, wave breakup. There are a bunch of feedback mechanisms. And I mean, on the left-hand side, you see in the magenta line, the definition of the marginalized zone based on concentration between the 15 and 80% concentration. In the yellow one is work that a colleague of mine is doing at the University of Cape Town, Marcello, which is defining the marginalized zone based on the natural variability of the sea ice, which is a little bit wider, and it's not based on sea ice concentration. Sea ice concentration is a little bit easier because you get that from satellite. And I also want to mention some of the work that Chris mentioned the other day with the ISAT2 by himself, and some of the work that Jill Brower did, in which she measured the extent of the marginalized zone based on the waviness of the area. And I mean, it plays a substantial role on the climate system. That's why we are interested in the marginalized zone. And so like, from a waves perspective, what generates waves in the Southern Ocean, that's a flume with a limited patch virtually, in which wind blows all year round in a clockwise direction. On the top hand side, you see the 50th percentile and the 90th percentile of the wind speed. So it's pretty strong in that area, in the Southern Ocean, where we have the roaring 40s, furious 50s, and screaming 60s. Gets windy out there. And you have this wind input that transfer energy to the ocean surface, and that's how waves are generated. So we have large waves all year round. These are the climatology for the summer, and you see that the 50th percentile is between 4 and 5 meters. And if you go to the 90th percentile, it's in excess of 9 meters, 6 meters, sorry. But this is the climatology, so it's an average of a month or so on. But what happens is that you have a number of intense events, intense cyclones, that continuously go around Antarctica in a clockwise direction. Usually have 3 at every given time around Antarctica, especially in winter. And here you see a evolution of a cyclone passing by Antarctica. This is in 2017. And those can generate, this is 4 different snapshots of 4 subsequent days. Like we have the intense one when you can see the track of the ship. I'll use the stick like the melody. Here the ship was entering. We were actually running away from a big storm because the captain said, let's get into the ice so we don't rock too much. And we had like waves that were about 10 meters outside of the sea ice when we were running away. And that's what happens in winter. So, and there are people from the ECMWF. This is a snapshot I took a few days ago from Windy, because they read whatever the ECMWF does, or you can select the source, GFS, icon, or whatever. And that's what I try to say, that are usually around Antarctica. You have 1, 2, 3 cyclones that are usually going around. Here, this is the prediction for this morning, and we had like about 9 meters here in this area of the Southern Ocean, in the Earth sector. And what the spectral wave model do is advect the energy. So this is basically how the wave energy in the third generation wave model moves. And on the right-hand side, we have the source term. The source term, it basically means how our energy varies according to input and dissipation mechanism. That's what Let did a little bit in her model. Basically, she's using that to generate waves, to model the waves. And we have some source terms here. So in a classical sense, you don't have ice. And so you have input due to the wind, dissipation due, for example, breaking. You have some nonlinear effect that it tells you how the energy changes. But when you have the ice, what you do is add sea ice dissipation that applies only on the sea ice concentration, Ci, and it doesn't apply on the open ocean sector. And what, for example, the ECMWF does, it's basically cut off the waves at 30% sea ice concentration. So it's usually a good idea to watch this prediction of ECMWF, because you have a pretty good idea about where the sea ice edge is, like all these large areas. So, easy peasy. Okay. Because I like to go to the Southern Ocean. I have friends in South Africa. They keep inviting me. And this is the picture from the 4th of July, 2017, memorable day for the Americans. They usually tend to remember that one. Also in that case, significant wave height was 4.6 meters. It was 100% sea ice concentration. It was mostly pancake ice flows, those little flows that form in winter. That's how the marginalized zone in winter looks like when it starts forming and expanding out towards the ocean. So it's not a compact ice cover, but it forms with the grease pancake ice cycle with those flows. And so those waves keep it in suspension and unconsolidated for a long time. This picture was taken about 44 kilometers from the sea ice edge. The maximum wave height we measure, so the maximum crest to trough of the wave oscillation, was 8 meters. And we published some of the results in Nature Communication recently. I'll send the videos. It's a little bit less clear, but you see those smooth wave front that are moving in that direction. Okay? It looks very smooth. It looks very calm. It was 4.6 significant wave, 6 meters significant wave height. Okay? I'll let you. Okay. Okay. And it's a mathematics conference, but come up from a background of engineering and oceanography and a little bit of everything. And the main technique that we used to operate back in 2017, and then we went back and operated it again and again to measure the sea ice properties, was like camera images, or like stereo camera images actually later. And so like one of the standard methods to classify ice is to put a human observer out there to do those so-called aspect observation, which is a standard that people do when they go down to Antarctica in a research vessel to qualify and quantify the ice properties. And so I use a quantitative metric in which I did some flow size reconstruction. Those are very small, so their average size is about 3 meters. I mean, most of the area, 50% of the area in that case, is comprised by flows between 2 and 4 meters. That's what you can see on the right-hand plot. And this is a typical condition for the winter sea ice that goes on for hundreds of kilometers in width. The rest, so like 60% is those pancake, of which most are 3 meters. The rest is fragile ice in between those pancakes. So the concentration in total is 100% sea ice concentration. So like if you remember the picture from the ECMWF, we did have 0 waves in 100% sea ice concentration. We don't propagate waves in that. And we use this system that we published recently in Nature Communication, in which we use those two cameras. So we use this telescopic camera reconstruction technique, which is based on a system that Alvise Benettazzo and Filippo Bergamasco developed in Venice, in which if you have two eyes, basically, you can have a sense of depth. And so you can reconstruct the three-dimensional surface in space and time. And this is a simple snapshot that I'm trying to show there. Ship is moving a little bit, as you probably have seen before. And so you need to do some correction, and you need to know where your eyes are. And so you put an IMU, so an inertial motion unit, that tells you how your frame of reference is moving relative to the ship. And then you can do some reconstruction, reconstruct the waves, and the wave spectrum. Here I want to focus on the main wave energy that propagates through the sea ice. So we did measurements along a transit from the sea ice edge deeper into the marginalized zone. This is the distance from the ice edge, 0 to 50. It wasn't really 100% in the first 5 kilometers, so that's it's a little bit shaded, but then it was 100% for real, the sea ice concentration, and as you saw in the picture. And the dots are the basically wave energy, normalized by the instantaneous wave energy that we had at the ice edge. And we took from the ERA 5. ERA 5 does pretty well. We verified it. And so we are happy with them. And the black line that you see there, it's a fit, an exponential fit. Okay? There are some papers, a big review of a lot of experimental results that came out from Alison Coates in 2020 recently, in which she revisited a lot of data sets, and she has a stronger attenuation compared to the one that we observed in the marginalized zone. And we were like, yeah, that's a little bit strange. We are in 100% ice. She has more dissipation than has. Ice condition or not. So what we did, because we had the full spectrum, so we could separate, I don't know, like what Chris did. If you have a spectrum, a direction spectrum, you can separate the wind waves, that are the waves that propagate along the direction of the wind, from other waves that are generated by the swell that was previously generated, and so they are not aligned with the wind speed. And so if you only consider the wind speed, we get closer to the prediction of Alison in 2020. But it wasn't that close. I mean, Alison says that we had about 20% of the energy after 50 kilometers. Our fit brings down 30%, so it's 1.5 times more energy that we have. And we're like, but surely, like, the surface wasn't flat. You have a certain roughness in there. So wind input, it's probably in there. You still have wind that pushes some of the energy. And so with a simple method based on like the extended fetch that we have, we take away the wind input in a very simplistic way, and we get way closer to what Alison was showing. And so that's what we wanted to model to a certain extent, and has been most of the work that I've been doing here in Norwich with Emilian. And because in a mathematics department, I have to show that I can do some mathematics. I started with some of the ideas. I borrowed some of the ideas from Mike Mailen, mostly. And so we started with linear waves with a viscous sea ice attenuation. Most of the theory is laid down in his JGR paper from 2018 that came probably out from the mathematics of sea ice in 2017. And so the standard hypothesis is that we have an invisible incompressible linear rotational flow in deep water condition. So you have a Laplacian, and you consider the sea ice cover as an homogeneous layer of constant average properties. Okay, that's our sea ice, that's on top. And so what changes is the dynamic boundary condition of the free surface. So what it does, instead of having air, so the atmospheric pressure on the surface of the ocean, you have an extra lid that adds a pressure due to the ice. So rho is the density, Pt is the derivative in time, and g eta is the gravity and the surface elevation. And so the added pressure is Pi. And this gives rise to the complex dispersion relation, where the real part is the dispersion relation in open ocean, the standard omega square equal to gk. the imaginary part gives you the dissipation, a frequency-dependent dissipation. So each mode eta hat decays exponentially according to ki, and ki is a function of omega. Ki depends on the physical mechanism that you adopt, and as Vernon showed before, most of the models are in the ballpark of 3, and so that's what we use. We don't care about this term, it's various CI's properties. Luke yesterday told us it doesn't really matter what CI's properties, and yeah, I don't want to focus on that one either. Okay, that's what Mike Malan did, and I have a background in nonlinear waves, and also in nonlinear waves you can model inviscid incompressible rotational flow. You preserve some of the wave nonlinearity in wave stiffness, so the product of the wave amplitude divided by the wavelength, or the amplitude and the wave number. And what you can generate is a standard model that's used by the nonlinear wave community, which is the nonlinear Schrödinger equation, the dNLS. This is not an equation for the simple surface elevation, so the fast-moving oscillation, so those waves, but it's an equation for the complex envelope B, so the one in the dark, the thicker one. So we are trying to model this one, which is modulated by the waves, okay? It's and in the literature for nonlinear waves with a viscous effect, you can add on the right-hand side a pressure that gives you some of the dissipation. This dissipation on the right-hand side is minus I KIB. And so what we did in a very simplistic way was substituting that right-hand side with the equation from Mike Malan. Simple as that. And we use that to simulate our condition that we observe in the Southern Ocean a few years earlier. And so what you need to do is have a boundary condition at the CI's edge for every time as x equal to 0. And so ER 5 was telling us that the wave height was about 7.3 meters, the wave period 12 seconds. And so they propagate from the open ocean towards the marginal zone. Waves are a random process. We saw some of the presentations that use a Johnson spectrum, some presentations that use a Pearson-Moskowitz spectrum. It doesn't really matter, to be honest, which kind of spectrum you use. You use a somewhat broad, somewhat narrow spectrum that reproduces the wave. In this case, for simple reason, we use a Gaussian spectrum. We use a standard approach in water waves, which is that the phases are random and uniformly distributed between 0 and 2 pi. Okay, so that's your shape of the spectrum. We simulate a domain that's 55 kilometers. Why 55? Because the first 5 kilometers are open water. So we start from a linear distribution of wave amplitude, so a linear condition, and we let it evolve in open ocean without dissipation for 5 kilometers, just to have a real nonlinear wave condition at the CI's edge. Okay. We use a delta x of 1 meter, a periodic domain in time, which is about 6,144 seconds. Because if you divide by the 12 seconds, it was a nice number to use the Fourier transform. And we advance in time, in space with a Runge-Kutta fourth order method. And yeah, that's why we use 6,144, because it's easier to do the fast Fourier transform, and it's faster. We did Monte Carlo random simulation, 10 of them. It was enough. We could have done more. We could have done less. Doesn't really matter. We have some standard parameter for the CIs, which came from observation that we did in the Southern Ocean, like the thickness of those pancakes were about 0.3 meters. The density ratio between CIs and water is about 0.9, doesn't really matter. And we used 2 values of viscosity. Forget about the number. Just remember there is a low one and a high one. The high one is just 10 times more. It basically means that in the low case and the high case, they have a ratio between the dissipation of 10. Okay? And so the complex envelope, the evolution in space on the y-axis and time for the 2 cases, the low dissipation and high dissipation is shown here. And as you can clearly see, in the low dissipation cases, we still have high waves further deeper in the marginalized zone. So this is our sea ice edge. Waves are going that way, and you still have quite sizable waves way deeper in the marginalized zone. If we use high dissipation, waves get dissipated way faster, and so the waves are way smaller when we get down there. This typical feature in this direction is because the groups moved with the group velocity. Okay, that's why they are diagonal. Okay, so the first thing that we did was looking at the wave amplitude, or some metric of the wave amplitude, normalized by 1, so it makes things easier. And we have the low dissipation here. This scale is a logarithmic scale, so here is about 0.8 at 50 kilometers. And the high dissipation is here, and it goes down to about 20%, which is what we observe in the Southern Ocean from our experiment in there. That's why the value of viscosity were chosen. So the high viscosity parameter was chosen to match the wave energy at 50 kilometers. Okay. On the bottom plot, what you see is the evolution of the peak wave period, so the most energetic wave mode. And you see that in low dissipation, there is a slight increase of the mean wave period. In high dissipation, this increase in mean wave period is way higher. Okay. We then compare our nonlinear model to the model of Melian et al., 2018. And this is a linear model, so it doesn't account for the nonlinearity. And as you can see, you still have this decay, which is not exponential, because otherwise it would be a straight line in a log plot. And we have quite higher energy, about 10, like almost double the energy that Mike has. And okay, so it means that if you consider a nonlinear model, you conserve more energy, and so waves are higher, deeper in the marginalized zone than a linear model would predict. So your marginalized zone, to a certain extent, is deeper than a linear model would predict. If then we compare to the values of the dissipation of the peak only and prediction of Ellison, we see that, I mean, obviously, because of the choice of the viscosity that we have, the final value is the same, but you see that the evolution in our case is simple exponential, so it's a straight line in a log plot, but ours is not. So it's more dissipative at the beginning and less dissipative further into the ice. So as we move further into the ice, it's way less dissipative. So the dissipative nonlinear Schrödinger equation preserves more energy compared to the linear model. I see Let is standing up. So I have, this was the most important results. Luke mentioned that this effect of the downshift is mostly due to the selective dissipation of the higher frequency modes, and you can clearly see here. So the low frequency modes are hardly dissipated, and the high frequency modes are dissipated way, way faster. Some people talk about extreme waves in sea ice, and that's probably one of the last points I want to make. And so what we look at is the exceedance probability. That's for low dissipation and high dissipation. So we start from a Gaussian sea state. We let it evolve in the open ocean. So we have the departure of the tail. That's the nature of the nonlinear Schrödinger equation. So it gives rise to extreme events. As you can see, the maximum elevation here. So it jumped up, and then it slightly decreases as we go along. But if you look at the exceedance probability deeper into the ice, you see that after the initial growth at the sea ice edge, when we move into the ice, it reverts back to the Gaussian process. So that means that there are no extreme events or extreme events beyond the Gaussian statistics in sea ice. And so that's basically it. That's what I want to say. We generated a toy model, a dissipative nonlinear Schrödinger model, and it shows a less than exponential decay and predicts larger waves compared to the linear model. But it also means that sea ice restores the Gaussian statistics. Thank you all for the attention, and leave you with some reference. Thank you very much.
Questions?
Oh gosh.
Thanks for the talk. So In the end, what can we learn from using the Schrödinger nonlinear equation on the physical? Sorry, what can we learn by using the Schrödinger nonlinear equation physically and the Malin term? Like,
it's basically what we can learn. I mean, I think the main result. I mean, I think there has been a lot of discussion about wave nonlinearity in CIs, and I think it went a little bit out of touch with the reality of the stuff because people use it to claim that there are extreme waves. The important results is that even if the steepness, so the parameter that regulates nonlinearity, decays deeper into the eyes, you still have some nonlinear effect. And those linear effects basically leads to a wave-wave interaction that leads to a momentaneous downshift of the energy. And because you have this exponential decay of the energy with omega cube, it means that they momentaneously downshift the energy to more conservative modes. And so it means that even if it's very small, it means that it's preserving way more energy deeper into the eyes. So the final results, especially for large C state, because let's be honest, these are quite large C states. It's that you end up with like, if you compare the model of Mike, we are 0.15 with ours with the same parameter of dissipation, we have about 0.25. So it's a 40% more energy that we have at 50 kilometers from the CIS edge. So that's basically means that our energy, it's carried on further and further. So it's a 50% difference at 50 kilometers. It's preserving more energy. That's basically it.
There's a question from Mike Malin online.
Oh my God. Hi, Mike.
I thought that the nonlinear Schrödinger equation was for weakly variable dispersion. So I wonder how you can include strong frequency dependence in the forcing.
Tell him that he has to wait for a year or so. We are going to use the modified nonlinear Schrödinger equation next. Yeah. Yeah, I'll see him next year when he comes here for the wave scattering workshop. Anything that more? Hi, Sasha. You can wait for me to go back to Norwich, you know?
Yeah. Just a very urgent question. If there are no ice, just no ice, can we use the same equation?
Absolutely, yes. Right? Absolutely,
but,
yes.
Then, Alberto, then the people should use it already. Right? Can you say something about the previous experience with this equation?
Some people don't like this equation, you know, it's a little bit too complicated when you start adding nonlinearity. I mean, if you talk to Letty, that's right next to you, in the spectral wave model, they have the source term as NL, and basically forget about it. The only difference is that from a forecast perspective, what you want to know.
I'm mainly concerned about the dissipation, because the rest is standard.
Yeah.
It's 400 years. But the dissipation, it seems new. And proportional just to B, it also seems new. So where it come from? Is it just from you, or it's from somewhere else?
It's borrow a little bit from people that use viscosity on top, and they do experiments. The Segura and Anderson group that have been doing a lot of experiments on the viscosity. So you sort of already have those damp and force nonlinear Schrödinger equation. The only difference is the shape of the dissipation. In my case, it depends on the frequency. So on the omega cube term, to be consistent with the linear theory that Mike derived.
Mike says this is an interesting direction to investigate, and he's sad he's not here.
Yeah, no, I'm sad he's not here as well.
So maybe this is a good point to stop for coffee and reconvene at 11. Yep. Let's thank all the speakers.